So this is the outline of a sequential circuit design. From the given problem description, we construct a state diagram. Out of the diagram, we derive a state table. From the table, we derive state equations. Then that's pretty much it. Out of the equation, you can draw logic diagram, which is a hardware implementation. So in the last lesson, we saw the very final step, the actual circuit, and then the previous stage, the state equation. So let me quickly recapture what we learned from previous lesson is that once the circuit is designed, then we can find the state equation such that the D flip-flop characteristic is that whatever is on D input will appear on output Q on next clock tick. So that behavior is described by state equation. So in state equation, we add over T plus 1, which means the output of the flip-flop on next clock tick currently is over T. So over T, the current value, we omit the over T part. So we only give over T plus 1 part representing the value on next clock tick. Since we have two flip-flops, let's label it as A and B. Then flip-flop input equation for flip-flop A is that on next clock tick, whatever is on current D will appear on Q, which is labeled A. So A T of 1 is whatever is on current D that will appear on next clock tick. So currently D has OR gate. So that is OR gate. The OR gate has two inputs. So first input is a product AND of current Q, which is A, and then the other input is X. So A and X is one of the OR input. The other OR input is X and the current value of a flip-flop B, so BX. So that's a state equation. So in actual design, we will derive state equations for flip-flop input, and then we are going to draw the circuit diagram. The reverse operation is also straightforward. By looking at the equation, since we have two flip-flop equations, so we will have two flip-flops, and then whatever is given, this one should be applied on input of the flip-flop. So this one should be on input of the B flip-flop, and then the last equation is for output, which is by this hardware described. So given the state equation, we should be able to draw the logic diagram, which is actual hardware implementation. Now let's go through the entire steps of a sequential circuit design. The very first step is from the given problem description, we are going to draw state diagram. So here is the example of state diagram. How do we construct such diagram from the problem description? We are going to study shortly. But suppose this is state diagram. Let's see how to interpret that. First, the circles are state. So we have four circles. So from this state diagram has four states. And then in each state we assign unique number, of course a binary number. So we assign unique number for each state. So the natural selection is a 0, 0, 0, 1, 1, 0, 1, 1. So we assign unique number for each state. So that is given inside the circle. So this the problem has four states, and then for each state we assign value 0, 0, 0, 1, 0, 1, 1, 0, and 1, 1. And then arrow represent the state transition, and then arrow has label some number slash some number. So what we give as label is some number is first one is input slash and then output is specified. So in this system, we assume that there is only one input. One input. How do we know it's a one input? Is that the left-hand side of slash is only single digit. So input, we are talking about all binary systems. So one digit input means one input only. So input is a 0 or 1. So what is described here is that when the problem or system is at state 0, 0, when input 0 is applied, it remains in the same state 0, 0. That's why we have a loop back, and then it produces output of 0. So we can imagine a sequential system which has only one input and then which has only one output, because after the slash we have only one single digit, and then internally it has four different states there, and then depending on the input, and then at the of course there's a clock applied as well. At each clock tick, this system changes its states or when it produces the output. That is described by this state diagram. So when the system is at state 0, 0, when input is 0, it remains with the output 0. But if input 1 is applied to the system, that it changes to state 0, 1 and produces output 0. When system is at 0, 1 state, when input is 1, it changes to state 1, 1 with output 0. When input is 0, when state 0, 1, it goes back to state 0, 0, produces output 1, and so on. So that is all described. As you can see, at each state, since you have only one single input, it has two possible arrows out of that when input is 0 or when input is 1. Only two possible outgoing arrows there. And then incoming arrow is we don't know how many would come, because from other state it would come. But outgoing arrow, you should have only two, because you have only one input. With the one input, you have only two possible choices, 0 and 1. So that is a state diagram. Once you construct the state diagram, then you can convert it to state table. That is quite a mechanical step, just do one by one. So here what you do is that since we have four states, and then to represent or to assign unique binary number in all four states, we need 2 digits of a binary number. So with the two digits, you can have a 0, 0, 0, 1, 1, 0, 1, 1, and each value represent one state. That's why we have such value here. And then those are states. States means something the system should remember. That is a memory. So memory is a state, and then this system remembers four different states. So this system should remember four different things. To remember four different things, we need two flip-flops. With a one flip-flop, we can store either 0 or 1. And then with the two flip-flops, we can store 0, 0, 0, 1, 1, 0, and 1, 1. So two flip-flops are needed to store, to remember four different states. So each flip-flop represents the position of those bits assigned for each state. So let's assign those one as A and B. So within two flip-flops, let's label as A and B, and the A flip-flop represents the most significant bit, left bit, and the B flip-flop represents the right bit position, and then depending on the flip-flops value 0, 0, 0, 1, 1, 0, and 1, 1, and then the system represents four different states. So state table is first figure out and label flip-flops. A and B represent the bit position of a state's number assigned there, and then had another column for input. So we have only one single input. And then next state, on next clock tick, what will be the value of a flip-flop? That's a flip-flop A becomes like this, flip-flop B becomes like that, and then what will be output? So that is a state table. So we will have a present state, the current value in the flip-flop. We have two flip-flops, and then with the input on next clock tick, the flip-flops will change its value to this one. That's next state, and then it produces output like that. So from this state diagram, we can construct such a state table. So Given present state, the 2-bit of a flip-flop is a one input, just list all possible values are 0, 0, 0, 0, 0, 1, and since we have 3 bits, we have 8 different enumerations are there. Then using that, and then using state diagram constructor, the right part, what will be flip-flop value A and B, and then Y on next clock tick. So how do we find that is that? So first row is A and B are 0, input is 0. So A and B are 0 means state 0, 0. When input is 0, this is the arrow. What it does is that it remains on the same state 0, 0, produces output 0. So it goes to 0, 0 state with output 0. Next one, when ABs are 0, 0 in this state, when input is 1. When input is 1, what you see from the diagram is when input is 1, we go to state 0, 1 with output 0. So we go to state 0, 1 with output 0. Next, when AB is 0, 1, this state with the input 0, we go back to state 0, 0 with output 1. So we go back to state 0, 0 with output 1. This row A, B, 0, 1, and this state when input is 1, we go to state 1, 1 with output 0. State 1, 1 and output 0. So the rest are pretty much the same. So let's take a look at next row. 1, 0, state, input 0. We go to state 0, 0, output 1. State 0, 0, output 1. 1, 0 with the input 1. 1, 0 with the input 1 remains output 0. 1, 0 remains output 0. When state 1, 1, input 0, then we go to state 0, 0 with output 1. State 0, 0 with output 1. Then finally, state 1, 1 with the input 1. We go to state 1, 0, output 0. State 1, 0, output 0. So that's how to construct a state table out of the state diagram.